last lecture we look at vector and two-dimensional motions. The two-dimensional motion it means instead of along a line, you're talking about, say, projectile motion, and later we're going to look at circular motion. And all this concept can be easily generated into three-dimensional. Now, today we are going to look at, have to say, is the key of the mechanics, and all of you will know. Now, if I ask you, if I say the Newton's law of motion, what come up to your mind? Come to your mind is F equal to ma. Yeah, most of you are very familiar with the second law. Now, today we are going to look at, first law and second law and the third law. And I want to clear up some of the concepts. Now, especially the third law, a lot of time it's not easy, so I would spend a bit of time to clarify what it means action and reaction. All right, so this is second law of motion, F equal to ma, and F itself is a vector, and A is also a vector. They are parallel. So this is what you will see. Let's start. There are three Newton's law and about motion. The first one, second one, and the third one. Usually just say 1, 2, 3. But sometimes if you really want to look at the meaning, the first law we also call the law of inertia. What it means, it defines something called inertia. Now it says it's easy. If you find an object and you check there's no force acting on the object, or if there's a force here, there will be another force. So it means the sum of all forces is 0. So this is the condition about this law. The second condition is, you say, when you look at the object, you have to set a coordinate. Now, it say if you are sitting or standing in this coordinate and you observe this object, and this object there's no force or the sum of the force equal to 0, and you will find either this object is moving at constant velocity or at rest with respect to you. You are the observer as frame. Now, the thing about this law is it's not all observer will agree the first law. Now, the first law doesn't say at rest or uniform motion. It means constant velocity. It just say or. So what it means is, if you are sitting here and look at this situation, if you are standing here and you find this object is at rest, so for you, and also you find the force, sum of the force 0. So you say now it's at rest, sum of force is 0. So you say yes, first law agree. Make sense? Now, if you find this object is no force, but it's accelerating, would you agree the first law? No, you won't. So the most important is whether you will agree, or you have to check. And just like any other law, you have to check whether it's agree or not. Now, imagine if you have a friend, your friend is sitting on the car, which is itself moving at 2 meters per second. Now, for your friend, how about when you observe this object, how will you say about this object? If you are standing, you are stopped, you are at rest, and you find this one at rest. Now your friend is moving at 2 meters per second in a car at a constant velocity. How would your friend tell about this object? It's moving. Moving at which direction? This direction with respect to him. So just like you are in a train, you are leaving the platform. You see the platform is moving backward. So what your friend will say is, yes, it's moving. So you and your friend is not agree. You say it's at west, and your friend is say the object is moving backward. But will you and your friend agree with the first law? Yes or no? Yes. Because the first law say either at west or uniform motion. Your friend will say at uniform motion. This time is backward with respect to him. So the key point is not the motion. It's not whether at west or moving at a constant velocity. It's whether you agree or not. So yes, you agree, your friend agree. And if you think about it, you have another friend. He's moving this direction, 2 meters per second. He also agree. So all your friends, as long as they are moving, even though they are moving at a constant speed, they will agree with first law. So we call this inertia. We call this inertia frame of reference. It means this is the privilege. This is a very good frame of reference. In such frame, Newton's first law hold or applies. Now, this your friend, and if once you find the first frame, any other frame moving with respect to this one at a constant velocity also inertia. So the idea of inertia frame or inertia reference frame is not one, is any is many. Actually, it's an infinitive. Any frame of reference related to this frame also is a inertia frame. Now, I'm going to ask you one. How about this time? If you have another friend, he's rotating. He's in a merry-go-round. He's rotating here. Will your friend this time agree the first law? No, it won't, because your friend will see it's rotating. So it means actually your friend will say this one, there's a centripetal acceleration toward him. So this is the thing is, it's not everybody will agree the first law. It's only those people, they are in a sort of privileged position. We call the inertia reference frame. They will agree the first law. So another thing is, if this time your friend is not just moving, it's accelerating, say with 1 meter per second square. Now you see there's no force acting on this one, but this time because your friend is moving to the right and accelerating, your friend will say this object is accelerating to the backward. Now in this case, the key is there's no force acting on this one, and you find this guy or this friend at C will find it move backward and also accelerating. You never know yourself is accelerating. So what happened is he would not agree the first law. So if you yourself is accelerating, the first law will not apply. Now the important thing is the object will remain at rest or keep moving at a straight line or constant velocity. We call this property called inertia because an object has inertia. So if I say the object has inertia, how can we measure the inertia? This is the second law. The second law have two aspects. Now we analyze the second law first. The second law say this one actually is sum of all forces. Now I give you one example. If you have an object here, if you have a F1 here, if you have F2 here, what you have to do now is you have to find the sum of F1 and F2 this way. So once you find the sum of F1 and F2, this is your F. So when you apply Newton's second law, you really have to find the sum of all four known forces on the object first. And then you say this object, because you have a non-zero force, the sum of the force is non-zero. So this is a vector. You also accelerate. The vector acceleration is parallel to this force and proportional to the mass. And this mass we call inertial mass. Now, what this inertial mass say? For example, if you have M1, M2, all right? Now, if it's subject the same force, 10 Newton, all right? Now, if you find the first mass, acceleration, so you got the acceleration. So it accelerate, the vector is 1 meter per second square. And the other accelerate as 2 meters per second square. Can you measure the mass from this experiment now? Yes, you can. So you can say the mass of the first object. What's the mass of first object you expect? 10, yeah, 10 kilograms. How about the mass of the second object? 5, exactly. So this is how you can use this equation to measure the mass. All right, and third law. The third law is law of reaction. Everybody aware is say action. Usually we remember action equal to reaction. Okay. Now I'm going to ask you one question. What it really means is this action and reaction is exerting on a different body. So what I mean, when you say about force, you usually say it's the two things. One is the source, S-O-U-R-C-E, the source, where the force come from. The second is on which object. So a force always have an initial, which one exert the force. And also there's an object which receive the force. Just I say, I give you money. So the money must be someone give and someone take. The same idea. If I say have a force, who give the force? Who take the force? Can you see the idea? Now, the idea is if this is Earth and if this is the moon, so you see the Earth will exert a force. So it say Earth is the give. This one, it take the force. So we'll say Earth exert a force on the moon, or if we put the article. So Earth exerts a force on the moon. So this is the give, this is the take. Now what the second law, not the third law say is, at the same time, if give and take, it just means if I give you $1, you also give me $1. Got the idea? So it means the moon also exerts a force to Earth. And the magnitude of these two forces the same, but these two forces, they are acting on the different objects. One is give from the Earth to the moon, so it's on the moon. One is from the moon to Earth. So they are at the different objects. Now, if the two forces acting on the different objects, can you cancel the forces? Now, I'm sure, can you vote this? Can you cancel the two forces, action and reaction? No, you can't, because this is action. This is your reaction. They are acting on different objects. So if there's a two object here, this is action, this is reaction. They are on different objects. Now, of course, you can say this is action and this is reaction. Same. It doesn't matter who is action, who is reaction. It's just a name. All we know is the force appear between two objects always is a pair.
But if one of the forces is smaller than the other?
No, they won't, because this is what the Newton's third law say. If the force exerted on this one is 10 Newton, the same magnitude will on this one, 10 Newton.
Okay, let's take friction.
Friction is a little bit complicated. We come back to this point. It's same. If the force from there on this one is 10 Newton, this one will also exert the friction on this one 10 Newton. Same.
Then why do we slip?
Why this one?
Why we slip if there is less friction?
We compare a little bit about the friction. Yeah, let's clarify these two things first. Okay. Now, look at third law. When I drop the ball, what is the force during? Ignore the air resistance. What is the force acting on this ball? Gravity. And we know how to calculate mg. For example, if this is 100 grams, and we approximate g as 10, so it's about 0.1 Newton. Make sense? So it means before it reaches the ground, there's a force which is 0.1 Newton acting on this one. Now, at the same time, the Newton's law says, the third law says, when it drops, the same amount, 0.1 Newton's force, also acts on the Earth. It means when it drops, it's not just this one come here, the Earth also come a little bit. Same force, same force. But think about it, it's the same force, but because this mass is very low, so you will see the acceleration dramatically. But the Earth is very massive. Can you see the acceleration? No, you can't. But it doesn't mean there's no force acting from here on the Earth. Can you see the idea? So it means this force, when we always say about the force on the object, we always have to keep in mind there's another force from this object to the other object. Force always appear as a pair. Always a pair. Got it? And also same magnitude. But how the two objects respond is a different matter. Acceleration is how you respond to the force. Same force, light, quick, very dramatic response. So it dropped. But so massive our Earth underneath, so it wouldn't see any respond to this force. So it doesn't mean there's no force. It's just you cannot see it. Another thing is we're standing on the Earth. So even though we respond, we won't know. How do you know? How do you know is this one drop here? It's not our Earth come to here. If you're standing on the Earth, make sense? So it may be it's an illusion. It may be because it's not this one drop to the Earth. It's during this time, it's the Earth come to here. How do you know we are sitting on the Earth? We're standing on the Earth. Can you see it? If the universe have no reference, you just don't know. Of course, we know it's dropped here. So yes, this is complicated. Now, therefore, I want to ask one question. How about some students always forget action equal to reaction, so they can cancel. So if you forget, all you need to do is do one thing. You hit the wall and ask yourself, will you get hurt? Yes. And then ask yourself, oh no, I give an action to the wall. It gives me a reaction to my bone. If they cancel, I shouldn't get hurt. But the fact, when you hit this one, you feel pain. There must be, you cannot cancel the two things. Make sense? And if you still don't believe, you stand in front of me and I punch. You will agree action cannot equal to reaction. You cannot cancel them. They're equal, but they're acting on a different objects. Make sense? So another thing is, how about this case? Now this is another case. Now, yes, remember I say during the process, this is action, this is reaction. They always exist. Got it? Now, how about like this? I stop it. Now, what is the force acting on this one? Gravity. The gravity still exists. Make sense? Now, the gravity exists all the way. Even though you stop it, the gravity still exists. Where the gravity comes from Earth. So what is the reaction force? From the Earth to here. So there's an action. What is the reaction? From this one to the Earth. Is this reaction force still exist? Yes. As long as the gravity exists. Like here, the reaction force always exists. So even though I stop it, don't forget the reaction force from here to the Earth still exists. Still exists. Now the problem is, it's not moving. So why? Because there must be the second force acting on the same object. What is the second force?
Normal.
From the book to the ball. Got it? But this is one force from the book to the ball. So this is the give, this is the take. Remember, there's a reverse. This will be the give. This will be the take. So it means at the same time, this force also exerts, this ball also exerts a force to the book. Now, if this book is very weak and this is very heavy, what happens? It goes through. Exactly. So exactly the same thing. If it's not able to give enough reaction force, we call this normal force. This normal force is another pair. Think about it. We have 4 different forces. Can you see it? In this case, how many forces? 1, 2. One is here, one is here. And here, how many forces? 4 different forces. One is the one to gravity, and the reaction force of the gravity is on the Earth, still acting on the Earth. The second force, the third one is from the book to here is the normal force. And also, this ball will exert a force, try to break through. So 4 different forces involved. Can you see? And it's the 2 forces acting on this one, make this one at rest. It's the normal force from the book to here, and it's the gravity from the Earth to here. They cancel out. Yes, there's a cancel out, but they're not action-reaction force. So if I draw this one here, this is how I usually draw. We look at here. Now this action-reaction always appear. Now imagine now this one is on the floor. So what happened is, during this time, the table will give you a normal force. Now sometimes we call normal reaction. I think the term reaction is very confusing. Yes, this is not a reaction force. Now, yes, reaction. It also this block and this object will give a force to the table. Therefore, your table actually will curve a little bit. So yeah, can you see how many forces appear? 1, 2, 3, 4, and the 2 forces they cancel out. It's not action and reaction. They are just coming from a different sources. One is from gravity, the red. The blue is from the table. So it just happened they are equal. Okay, make sense this one? If you make sense, everything now is make sense. When you kick the ball, you give the ball a action. The ball gives you back a reaction. Therefore, you feel hurt. But the ball will fly. There's a different problem. It's a different story. You stand here because you got the gravity, and at the same time the floor gives you normal force. They cancelled out. The same thing here. When the blue car hit the yellow bus, the blue car exerts a force to the bus, and at the same time the bus exerts a force to the blue cars. The blue car is so small, therefore you will leave a dent, or also it will damage the blue car. But whereas the yellow bus is so massive, it won't damage much, and also it's strong usually. One reason we can walk is because there's a friction. You push the ground, so the ground will a little bit deform, and then the ground will give you a reaction force, and this interaction is friction. Okay, so friction is the reaction force from the ground to you, make you walk. Now there is a limitation how much friction it will supply push you. Therefore, it's not about how much you can push, it's how much the friction can give you, and there are action and reaction. So it means if the material very slippery, or you put some water here, the friction just not enough. It means you are just not able to push forward. You just cannot push. Okay. And remember, when you push, you have to have two components. I'm talking about this component. I think this is what the confusion arises. You push downward. Now there's a two component. One is here, one is here. This is the one you push down. This you also have reaction force. I mean, this is always. But whether you got the component here, friction, push you forward, is another matter. And is this component related to this? Later we learn. So is the friction, is the forward friction important? So the reaction force have two components, and one is react to the normal down, one is reacting to the sideway. And if the material cannot, you cannot give this one. We already mentioned all the remarks, so please read. Inertia frame, we call this sum. Later when we work in the one example, we'll know how to do this one. And another thing is this law, F equal to ma, can be written in another form. Remember, A is delta V, delta T. So you put the M here, so it's mv delta T. You group this one, and you tell this one is called P. So F can be written as change of momentum. And this form is what Newton wrote when he published his theory. It means Newton didn't write F equal to ma. He used this one instead. They're equivalent. How many different forces? Can you name how many forces you learn? Can you name some forces, the name of the force you learn? Gravity? What else? Friction. Come on, what forces you know? The name of the force. Tension. What else? Centripetal force, yep. Sorry? Air resistance, yep. Now, so far so good. So let's list it. Now I list 4 here. I add some tension, air resistance, what else? Friction, centripetal force, okay. With magnetic, agree? And static. Now, I will say, yes, we have so many forces, but a little bit like science. If I ask you how many English words we have, 100,000. How many alphabet? 26. So it means you can make up many word with only 26 alphabet. The same idea, you can make up all these forces with only 4 different forces. So what I mean is that just like alphabet, there's only 4. They are fundamental. And the rest is just a combination of all these 4 forces. Now, let's look at the tension, where you got the idea of tension from. You have a string, make sense? And you try to push it. So if you look at the atom here, actually when you pull the string, the atom A, atom B, if you make a magnify, they have a bonding, they have a chemical bonding, and this chemical bonding is the one holding your tension, holding your string. And this chemical bonding intrinsically is belong to electromagnetic. So whenever you involve chemical bonding, they are electromagnetic. So yes, tension is electromagnetic. How about air resistance? Air resistance in a way is also electromagnetic because it is outside the air molecule interact with the body's molecule. So all this is also electromagnetics. Friction for sure. When you have a rough surface, these atoms and these atoms, they form bonding. In order to break the bonding, you have to apply a shear force. And this is where the friction comes from. So friction is also electromagnetic. So you see a lot of force, their origin actually is electromagnetic. Gravity, of course. So what we usually see is gravity and electromagnetic. Now, magnetic is also electromagnetics. Now I want to highlight one force, centripetal force. Centripetal force is not a force. We'll come back to this statement. This is a very interesting statement. Centripetal force is not a force. Centripetal force is the road of the force. I use this example. Teacher, okay? Teacher is not a person. What I mean is anyone can be the teacher. One day you may be standing here, you will be the teacher. Someone, if I'm ill, someone will come here, replace me. So whoever standing here, he or she is the teacher. Got it? So teacher is just a road. It's just a road. And also this road disappears once we live here, once I live here. Once I go home, I'm not a teacher anymore. Same, centripetal force is not a force. You have to find someone, the will force, to act as centripetal force. Can you see it? So a little bit different. So centripetal force is just the name, just the label to one of the force when the force try to keep something circular motion. Now, to make something in circular motion, it can be tension, it can be gravity, it can be magnetic. I've got it. So any force can be centripetal force. Force is a vector. This is important. Therefore, looking at here centripetal force, because when this one move with v, the velocity change. So the acceleration is here. Therefore, we know the force must be here. They are parallel. So it points to the center. It points to the center. And this is what we call centripetal force. Now, which force have this act, or which force become the centripetal? It depends the problem. If you are the sun and the earth, which is the gravity. If this is a proton and this is an electron, this is electromagnetic. If this is a string, it can be a Hooke's law. So it can be any force. Now we are going to look at some more concept. Weight. Now under the earth, we will also say what's your weight. And if I say what is your weight, usually how will you respond to me? Say for example, if somebody asks me in the street, I will say my weight is 70 kilo. Got it? It's exactly what I weighed yesterday. So 70 kilo is my weight. Do you think this statement is something odd in science? Because we defined W is mg. So W is a force. It's just we give a special name for this force. We call W. And W is the weight. So ideally, what you're saying is, my mass is 70 kilogram. Because the G is about 10, I use 10 in here. Therefore, the force acting on me by the gravity is 700 Newton. So I have to tell people my weight actually is 700 Newton. Make sense? But do you ever do it? No, you never. Why? Because this is sort of, again, science. The way we use language is very different from people. They don't learn science. We are using a language in a more restricted, precise way, which we can communicate with engineers and scientists. Got it? So whenever you say, what's your weight, it depends on who asks you. If asks you is the professor, you have to say you're 700 Newton. If it's someone, they don't know science, don't do it. Otherwise you're a little bit arrogant. You try to sort of show off. So they just say 70 kilogram. All right. So remember, a lot of time, it's not how much you know, it's who's your target. If your target, she or her, doesn't like science, think about it. If you keep bombarding your friend with science, what happens? Your friend will leave, whoever. So don't worry about it. Depend on who you're talking to. You use the language which suit the communication circumstances. Now, let's clarify another thing is, if you stand on the bathroom scale, and the bathroom scale gives you 70 kilogram, agree? So what's actually doing? I will say the bathroom scale. Now think about the physics. The physics is, under the bathroom scale, it has a spring or a sensor, electronic sensor. It sends what? It sends force. So what from the compression, delta X, so use Hooke's law. You see the old bathroom scale, use Hooke's law, work out the force from the delta X. Got it? Now, after you work out the force is 700 Newton, the manufacturer convert the 700 Newton divided by 10 and display 70. Make sense? So it all depends on what? The conversion factor. Now think about it now. Instead of Earth, if you are trying to use the same bathroom scale on Moon. Now first of all, G is not a constant. On Earth, G is 9.8 meter per second square. On Moon, the G value is about a sixth. Okay? I think it's correct. Now, can you check it? Can you check the Moon, the gravity of Moon? Can you confirm to me? 1.6 multiplied by 6. Yeah, it's about 1/6. Got it? So it's a 1.6. It's about 6. Now what I mean is, now how about your force? Your force actually is less. Your force on you. So the gravity acting on you is not 700 Newton this time. It will be divided by 6. So it's about 120 Newton. Got it? Now, because the force is less, the delta x also less. So the delta x will be only a sixth of the original. And therefore, it will, because you are less force, but this one still divided by 10. So your displaced will be what? 12 kilogram. Can you see it? So the question is your mass on the surface of the moon really 12 kilogram? This is what given by the bathroom scale. Yes or no? The mass, remember, mass never change. So what problem here is the 10 here. If you really do this experiment on the surface moon, are you able to use 10 here? You must use what? 1.6. So it gives you the mass correctly. So it means it's the force calibration of your instrument. Can you see it? Now, your mass will not change. You will only give always 70 kilogram. Now, therefore, if you really talk about weight, what is your weight? Your weight now become 120 Newton on Moon by weight. And on Earth, by weight is 700 Newton. So you see, when I say you lose weight, if I want to lose my own weight, it's easy. All I need to do is what? Go to the moon, yeah. My weight lose, so I don't need to pay $1,000 for anyone and say you can lose the weight guarantee in 2 weeks. I can always go straight to the moon in 5 days.
So they pay millions to...
Yeah, I will pay $1 million. Oh, anyway, I can lose weight easily. Okay, but how about my mass? My mass never change. So 70 kilogram will not change. So remember, when you lose weight, I mean, if you really play trick, you can always lose somebody's weight easily. Even by sending somebody high in the mountain and look at the gravity, it's less. So losing weight is easy. Losing mass is hard. You have to burn your fat. And remember, 1 kilogram of fat, you have to generate how it equivalent to about 700 calorie. Yeah. 7,000, I beg your pardon, 7,000 calorie. And if you run 10 kilometer, you probably lose 700. So how long have to run in order to lose 1 kilogram of fat? 100. Not a bad thing if you keep running 10 kilogram a week. 10 weeks time, you lose 1 kilogram. Why not? So yes, this is the best way to lose. There's no alternative. This is all science. This is all science. Okay? There's no alternative. There's no alternative. You have to burn the fat. And you know how the energy of the fat, 1 kilogram of human fat, how much energy you have to generate. It means you have to burn it. Okay? All right? That's why I keep running. There's no... Now, another thing I want to clarify is the G, is the value of G. Going back here, how do you get this G anyway? Why 9.8? Now, let's look at the problem. This is the Earth, and you are standing here, agree? So you are close to the RE, the R of radius, and RE, the radius of Earth, about 64 kilo, this one. Now, you are going to say F equal to ma. So what is the acceleration here? So you say, all right, you know the mass. What is this one? But what is the force? The force here is G m r e squared. This is the universal gravitational law. Okay, this is the gravity. And this one is your F. And when you apply this law to you, you see both sides, the left-hand side and right-hand side, have mass, your own mass. So your own mass actually cancelled out. It doesn't matter your mass. the acceleration here. Now, if you plug the value of g, this g is a true constant. This is a real constant. The capital G is a real constant. This is the mass of Earth. This is the radius. When you plug all the number into here, you got 9.8 meter per second square. This is where it comes from. Now, if you notice how this number comes from, you look at how to make up the number. G is a constant. M on Earth is constant. But how about here? This one is not constant. What I mean is, now if you are in 10 kilometers, you should expect the R is bigger. Therefore, your G value is lower. Make sense? Now, how about if you go deeper? You drill a hole into the ground, because now you are using the mass of this mass. So this time is both the R reduces, but at the same time the mass also reduces. The R reduced to the power of 2, the mass reduced to the power of 3 actually, because of the volume. So when you go down, this G value become less. Now this is important. If you are able to drill a hole and measure the G value at different points, do you know what you can get? You can really deduce is the M. What is the mass surrounding you? And from here, you can work out the geologic information, geology, okay? The geographical or geological information. It means what material surrounding you. And from here, the instrument is very precise and sophisticated. If you are able to do this, this belongs to the job of geophysicists. And you will get employment from mining company and also from petroleum company. They're looking for geophysicists to do this sort of job. They measure the G value, precise. From here, you know how to deduce what is going on with surrounding and what might you expect you have. Because think about each material have different density. So you're talking about very, very precise measurement. And remember, if you can handle this equipment, you know how to interpret the data. You get $100,000 job per year. It's easy. It's easy in Australia, and it may be even bigger. So it's a very valuable skills, all based on science again. Mass and weight we already discussed. Hooke's law. We're going to look at several laws and look at the detail. What's the negative here means? It means, now let's look at it. If this is a spring, we say this is 0. Now if in case 1 you extend this one, so you measure the 0 to here, this is delta x. The delta x this time is positive, agree? So what is the force acting on this one? Negative. So the direction of the force and this one, they are proportional, but negative. Inverse, not inverse, opposite. Now, how about this time you compress your spring? Now, because you measure from here, your delta x this time is negative. You measure to the negative side. So F, but the force is positive. You push back to the positive side. So again, minus k delta x, if this one is negative, negative, this one will be positive. So it doesn't matter which side you push. The negative here, it just means the force and displacement are opposite to each other. All right. So the negative sign is not a mathematics, it's a physics. Can you see it? It tells you the two quantities, they're always opposite to each other. Normal force, yes, I just use this one example. when you drop, you have a gravity from the earth. This one is from earth. When you stop by the table, you got another force. So now you have one force up, one force down. This is from earth. This one is from table. You see the source, they are different. They are different. But they're acting on the same object, the bucket. Therefore, it doesn't move. It stopped moving. All right? Tension. The same, remember I say tension is due to the molecule, the chemical bonding. So if a little girl hanging here, the tension on her is up because it's balance, it's weight. At the same time here, this joining point here, the tension on the beam, on this beam here is down. Got it? And the beam on the tension is also up. You try to drag it up. So they're balanced, of course. Friction. We're going to look at friction next week in a more detail. There's two types of friction. One is kinetic, one is static. We'll also do an experiment next week on friction. Okay, we look at fluid in week 6. So I wait until week 6 to look into. It just demonstrates there's so many different types of forces. And one of the forces is the drag. It means resistance. Resistance is always proportional to velocity. So think about G, mg. mg is always the same. Can you see it? But if you drop the ball, if there's an air, when it drops, when the moment the ball leaves my hand, the moment there's a no velocity, so there's no air resistance. But because the velocity keep increasing, so the air resistance also increase. So until the point, so you can say there's a little air resistance up. At this point, the air resistance get bigger, and at this point, the air resistance actually balance. So once you reach this point, the air resistance, the drag force balance the mg. Now the sum of the force is equal to what? 0. Once it's equal to 0, delta v, delta t equal to 0. That's solution. So once you reach this stage, the drag force and the mg, they are equal. A is 0. It means v become constant. This is where make you safe when you have a parachute. So the parachute will increase the drag force and try to make the drag force as equal to the gravity as soon as possible. So the terminal velocity, we call the terminal velocity, will be less. So we won't, when you hit the ground, it won't get hurt. Incline, when you have lift your object in the incline, you have to usually, I'm not saying you must, but usually you will resolve this mg into two components. One is along, one is perpendicular. And if this is theta, this is also theta. This component is mg cosine theta. And this component is mg sine theta. And you see along here, so this one is equal to mg cosine theta. And along this direction, we call the x, there's a no force stop it unless you have a friction. So therefore your object will slide down. If there's a friction, the friction here opposite is equal to mu Fn. It means the friction is mu mg cosine theta. All right. Now, problem with solving strategy. First is a good diagram, picture. If you were in my tutorial, you know how much I address to making a good drawing. And on the drawing, you find you draw the so-called free body diagram. It means you want to look at the force. And then you apply second law on each object. Now, 1, 2, 3, I want to apply the 3 steps in this example. 2.4. I will give you about 10 minutes. I want you to look at this example together. Now remember, the first is drawing. So I already give you the drawing here. Second part, if you isolate, I call this M1, I call this M2. You isolate the 2, and I call this M1, I call this M2. And you want to find so-called the free body diagram. The free body diagram only shows the forces. All right. So I let you do it. You want to find the acceleration. Now, if you have your note, if you print out your notes, by all means, you just work on the notes. If you don't, can anyone just I will give you some paper. So I will give you here. All right, I will get some paper if you don't have your. Now, we do it one by one. Now, first analyze M1. How many forces acting on M1? Anyone can tell me? How many forces acting on M1? 1, 2, 3, 4, all possibility. Now, first of all, whenever you have a mass, you always have what? M1G. Now, think about this just like an object. If an object sitting here is not moving up and down, so it means the sum of the force, at least along here, is 0. Why? Because there must be a normal force from the table to this ball counter the mass. So therefore, you have to draw the other force, which is usually we use N. Of course, you know the magnitude of the M must equal to M1G in this case. Now, you have this object M1 attach a string. Now, whenever you attach a string, especially if this string is under tension, like here, under tension, that means must be a force. Make sense? So we usually say if this object attach a string, there will be a tension. The tension is along the string, and the tension want to drag this one down. Of course, this one is T. Now, this is the force diagram for M1. We have to separate the force diagram on M2. So M2, how many forces acting on M2? 1, 2. Yes? M2, remember the string here, but for M2 here, this is M2. Now, think about the magnitude. First, how would you expect M2? Will M2 go up, stay behind, stay at rest, or go down? It goes down. For sure, it goes down. So it goes down, but how about the force? The gravity is always down. But when you're holding this one, for this one, this force actually try to hold it up. It's just because this force tension on the M2 is not big enough, and the mass is higher than the 10T. So therefore, we have to draw the 2 arrows. One is M2G, and the length of T must equal. It means why? Because along the string, the tension must equal. If, as put it this way, The tension is equal if the mass of the string is negligible. When you do mechanical engine, one day you will look at, you have a huge cable. When you try to calculate the string of the cable which hold the bridge. The cable itself is not negligible, the mass. So in this case, the tension, every point is different. So I just want you, a lot of things we are doing is under a very simple assumption. Now, this T is up and the T is less. Can you see it? Now, once you finish this tool, what we need to do is apply, remember the strategy I say. Draw a good diagram. Yes, we done it. Free body diagram. Yes, we done it. Write the Newton's second law for each object. So it means how many objects you have? Two. So how many Newton's second laws you have to write? 2. Can you see it? Now let's look at write M1. Now M1, to be honest, for M1, you need to write 2 second law. One is up and down, one is horizontal. But because we know up and down, they cancel out. So we don't need to worry about up and down. We only write the Newton law along the horizontal. So how will you say it? Along horizontally, how many forces? Only T. So we first write F equal to M1A. This is the general form. Now you say, in this case, the force is the tension. Got it? So you specify. We call the equation 1. How about the same here? The second law for M2A. Now another thing is, can you see I use the same A? Why? Because they are connected. The two objects are connected. Make sense? If this is accelerate this side 1 meter per second, therefore also 1 meter per second down. So the A, the magnitude of the A must be same. Now, how would you write this one? Remember, this also means the sum. You have 2 forces. Which one is bigger, M2G or T? M2G. So when one is down, one is up, when you just look at the number, forget about the direction. Which one's bigger? The down is bigger. So when you say the sum, it means this one subtract this one. So like an algebra. So the sum of the force is M2G minus T. Can you see I replace the force by 2 forces and find the sum? And though in this case, when I say sum, actually it means subtraction. Equal to M2A. Now this is second equation. Now look at here. How many equations we have? 2. How many unknown? Now we know M1, we know M2. So how many unknowns? T and A. Remember your math teacher say 2 equations, 2 unknown. Can you solve them? Yes. So we stop here because they are the math. No, you don't want me to stop. You want me to show you how to do it. All right. So yes, as a physics teacher, I will comfortably say I will stop here. But I want to go ahead. The reason is what? It's not the math, it's the physics. So what I want to do is, I want you to not, now you may, most of you at this stage, will try to plug the number in. Now can you do not plug any number and you try to find A without any number? It means your expression of A should in terms of M1, M2, and G. Can you do it? How would you do it? Now this is a bit of skills in math, and this is important skills. I want you to learn how to solve an equation without any number. Come on, do it. Try to solve it. Yep. The two equations. List the two equations. Think about how you do it. I will do some less. Anyone still need a paper? Yep. Maybe you want to do it on the paper. Yep. Yep. All right. No worry. Do you need a paper? Try doing here. Yep. You finished. Good. Well done. Now, may I suggest you substitute 1 into 2. Okay, come on. What it means substitute 1 into 2? It means now you replace, instead of t, you put m1a, replace the t. Got it? Come on, do it. You need the mass, remember. Okay, when you substitute 1 into 2, you got m2g minus m1a equal to m2a. Now, remember, don't forget your aim. Your aim is find a. So, highlight those terms which have a. So, this term and this term. So what's the strategy? What's a high school teacher tell you? Once you highlight the term which you have the unknown you want to find, you want to group the term. Got it? So there's a different way. It doesn't matter which side. So for me, I can put this one here is easier. So I say m2g m1a plus m2a. So now you have a common term. So get the common term, m1 plus m2a. So what you get is, I swap it. So a is equal to m2, m1 plus m2. Now, can you see the way I write down the solution? I deliberately group all the mass into a bracket. Can you see it? So what it means. Now, the advantage, you see, this show all the advantage. First, this is meter per second square. This one is meter per second square. And if you look at m2, m1 over m2, this is kilogram. This is kilogram, so they cancel out. So this is only a number. This is a number. And also, can you see m2 divided m1 plus m2? This number is always less than 1. So what you're saying is A always less than G. And it makes sense, because if there's nothing holding this ball, it just drop G with acceleration. But when you have a string, try to pull it up. So this force is, even though small, but at least it counter a little bit the gravity. Therefore, the overall acceleration is less than G. And think about it, what happened if m1 becomes 0. It means you remove this one, you cut this off, so m1 is 0. m1 becomes 0. m2 over m1 plus m2 equal to 1. Therefore, A equal to G. Make sense? Now you see, I come to all this conclusion without a single number. There's something you must learn. You don't need number to learn physics and to learn engineering problem. Once you finish all, the last stage is really plug the number in, of course, which is 1.2.5, 1.5 plus 2.5 multiplied 9.8. That's it. So we wait until the last minute to plug the number in and get your numerical solution. And before you do it, you already check all the circumstances, all the special case, and you find your formula is correct. All right, so we stop here today, and there's a second part which has a friction. I challenge you. The second part has friction, so maybe I give you a hint. Now, if the second part has friction, the only thing different is this law is T minus 8.5 equal to M1 equal to M1A. And the second equation for this one still M2G minus T equal to M2A. So you only got a extra number. And from here, it's a little bit more complicated. T is equal to M1A plus 8.5. And I let you do the math. The math is not difficult. You just will do the same thing, solve the A and find the T. All right, we stop here, and I will let you do the attendance.